All right, so we had covered these points and topics before yesterday in the previous lesson, and we were at this point, relationships from planetary data. So, what he's expecting from you is that we will discuss all of these things, of course. What he's expecting from you that looking at this data given in the question, sometimes a few things will be given, sometimes all of them will be given. So all the data will be given to you, and he will ask you to predict a few things about this setup, or at least about that planet. So, for the sake of example, let's develop a few relationships before moving on to the conclusion. This all the conclusions of the topic are written in this slide, but let's go back and try to see and develop some trends based on our own idea that what are we seeing right now. So, let's compare the distance of that planet from the sun and the orbiting time it takes for that planet to complete around the sun. So, look at Mercury. So Mercury is very close to the Sun in comparison to the rest of the planets. It is the closest one. So it takes approximately 88 days. So its orbital speed would be quite high because it is closer to the stronger gravitational field. And we discussed this point yesterday in the previous lesson that if you are closer to the Sun, you will be moving faster, and if you are away from the Sun, you will be moving slower. And this results in a lower orbital speed and a longer orbital period. That is what we concluded yesterday in the previous lesson, right? So now we can see the evidence as well that the planet that is closer to the Sun is taking less time to complete its orbit. And it has, or we will find its orbital speed to be larger or more than the rest of the planets. Now let's compare Venus with the orbiting time of the Venus around the Sun. No doubt the orbiting circle or the circumference is larger, but just because it is moving away from the Sun, its orbital speed is reducing because the gravitational attraction is less centripetal force leading to less centripetal acceleration, eventually leading to smaller answer of velocities. So down the line, I see the trend that I'm seeing right now is that if the distance increases, the time is decreasing. So they have an inverse relationship amongst themselves. So if Uranus and Neptune are very far away, they have their orbital periods proportionally very, very large, right? So, sorry, it's going to be a direct relationship, not an inverse relationship. It's going to be a direct one. Okay, so if the distance from the Sun increases, the time taken for these planets to orbit the Sun also increases. And we can say that consequently, the orbital speed decreases. They are moving slowly in comparison to the planets that are closer to the Sun. Okay, so the rest of the parameters, for example, the density, diameters, masses, they are relatively comparable, and we can see that planets split by the asteroid belt are Mercury and Mars up to Mars, and from Jupiter to Neptune we see that they were the outer planets. So they will have something similar. They will have higher densities, they will have lower densities but high masses because they're generally made out of gas clouds, which we did yesterday. And the inner planets will have densities very closer to each other, or the values of densities to be very close to each other. As we can see over here, that up to Mars, the density values are very close to each other. Although the density of Mars is much less than the other planets, but approximately if we see across the board, they are the same. But as we move on the outer side, we see that the gas clouded or at least less density planets are on the outer side of the asteroid belt, which were of course in the previous lesson we discussed are made out of basically dust and gas cloud. So these are the ideas and relationships we can deduce from this table. Let's go on the next slide and see. So a planet here increases with distance as it moves further away. For example, this is the Sun. These are the orbits. So this orbit will have a smaller time in comparison to this one. So as far as they can go, their time will increase. They will have to cover a larger orbital radius. or circumference, which ultimately will cause a larger orbital period. And the orbital speed decreases, which we have already discussed. Okay, so there's one anomaly about the temperature. If I see that if I move down the line, generally the temperature decreases for that respective planet. But there is only just one anomaly or one anomalous point, that is 460, that is coming from Venus. There is a reason for that why Venus experiences such a high temperature is because its atmosphere is concentrated with carbon dioxide, which is a greenhouse gas, right? So it absorbs a lot of radiation, stores that energy in the planet's system as a greenhouse effect, and eventually causes its temperature to be even higher than Mercury. Although Mercury is closer to the Sun, but even its temperature is even higher than that. So it's something to do with the atmosphere of Venus. Other than that, if we are moving away from the Sun, our general temperature of the planet is generally decreasing. Okay, so another thing, that Mars is also tilted at 24 degrees, just like the Earth. The Earth has tilted at approximately, I think 21.4 or something like that. Mars is also tilted on its own axis, which is why Mars also has seasons, just like the Earth does. Okay, so these are the summary of all the points that we have discussed before. I will send you the slides, and then you can, and also the notes of the chapter, then you can make these notes on your own. Again, the whole chapter is based on memory, nothing more than that. So now we're going to start stars and the universe. We're going to discuss about our own star, which is the Sun, and so on and so forth. So what is required by you is, what you need to understand and remember is that what we have done in the previous chapter when we were doing radioactivity is that how stars are formed, at least discussed how fusion takes place on the Sun. So this is what's happening on the Sun at all times. So two hydrogen atoms are fusing together to become helium, which is generally an alpha particle because there are no orbiting electrons around it, right? And it releases a lot of energy, which is the cause of the radiation, or you can say the energy, all the energy content coming from the Sun. This is its reason. And all the theoretical discussion you will find will be on this page. And stars have different sizes, they have different masses, and even their surface temperatures or inner core temperatures are different. But how they are formed is will be discussed in the next point or in the next slide. Just a brief idea before we move ahead on the formation of star. You see, star formation requires high pressure. These are your marking scheme answers. They require high pressure and high temperature to actually form or exist or be born in the first place. So we have, let's say, when hydrogen atoms are coming close to each other to fuse together. The question is, why are they coming close together in the first place? Because both are positively charged. What's pushing them together? So actually, the gravitational attraction on each of these particles is trying to bring it closer. So when gas particles from distant, let's say they are distant from each other, they start collapsing on each other like this due to gravitational attraction, and they start collapsing because of the gravitational attraction, and in doing so they gain, or you can say that the gravitational potential energy is converted into kinetic energy. And we know that from kinetic model of matter, kinetic energy of any system or any particle is proportional to its temperature. So if the kinetic energy is increasing of these molecules, I can say that the temperature of the system is also increasing. So we find high temperature because they are collapsing onto each other, and we find high pressure because gravitation is trying to push or trying to pull in everything together. They are trying to repel each other, but at this moment, extremely high temperatures, extremely high pressure, high mass of the system producing high gravitational attraction actually overcomes, or you can say dominates the system, and this repulsion is not good enough or to stop it or stop the fusion from happening in the first place. So we end up creating a star. So once this happens, let's say when the fusion does take place, there are two things happening at the same time. The outer mass of the cloud or the gas still wants to collapse. It still wants to collapse because of the gravitational attraction. So that is the inward pull of gravity, which is always there. This balance will always be there. But since at the very core, everything is fusing together to become helium and releasing a lot of energy, this releases explosive energy that is exploding or pushing out on the boundaries or outwards in all directions. So this is the explosion due to fusion. Explosion due to fusion energy. This is generally also referred as radiation pressure. You may research about this, right? So why is our star, the sun, being stationary or at least existing the way it exists? Why it is doing that? Because its inward pull of the gravity and the energy released from the explosion are completely balanced. So whatever is trying to pull it together is being compensated by an equal and opposite force trying to negate that, which establishes an equilibrium, and then a star is born, or you can say star starts living. Now, what causes the death of the star? Why does it die? We will get to that later. But this is the idea behind the birth of a star, right? Okay. Now we're going to go towards the galaxy. These are the points of your syllabus, what you're supposed to know. We have stars, and the nearest galaxy that we have is Milky Way, right? This is what Milky Way looks like from Earth. This is what we see on a clear sky or on a clear day. This is what we can see. And this is another image of the Milky Way, right? So one mathematical calculation that you might have heard online as well, or mathematical word at least heard online as well in some research, or let's say some YouTube videos or in any other resource, is the term light years. What is the meaning of light year? You see, the distance or the astronomical distances between one galaxy and another galaxy is so great that we can't use general measurement of kilometers to actually represent that. So what we have done, we have devised a new unit of distance. Light year feels like that it's some time. We are discussing about time, but no. Light year is actually a quantity of distance. Is actually representing distance. But how much distance? It says that if the light itself, keeps traveling for 1 year, the distance light would have covered would actually be equal to this quantity, which is a very big number, extremely large number. So you can verify this and calculate this on your own simply by using speed is equal to distance over time, right? So we know that the speed of light is 3 into 10 to the power 8 in vacuum. The distance is what we need to find out, and the time would be for 1 year. So 365 days multiplied by 24 hours multiplied by 3600 as minutes converted into seconds, right? If you bring that number on the other side, the value that you're going to get is 9.5 power 15, 10 power 15, right? So this is the distance represented as 1 light year. Now just imagine that the distance between galaxies, the nearest galaxy, is approximately 1 billion miles. It's approximately 1 billion light years. Now, just to put it into perspective, this distance, let alone, is infinitely larger, and even so, this is represented as 1 light year. And the distance between the galaxies is, let's say, for the sake of example, is 500 light years. Now just imagine how great or how great this distance is. So for astronomical objects around the solar system, in the galaxy, towards another galaxy, and neighboring galaxies, that is measured in light years, right? So the 1 light year will be equal to at least this many kilometers or at least this many meters, right? So it's convenient for us to write down 1 light year instead of just writing down this number. It's understood. So again, it's based on convenience. So this is how a star is born. whatever I've discussed, this is going to be in the same state. So let's discuss a few ideas that intrigue at least a question: why is everything happening? So it starts from clouds and dust gathering together that have hydrogen. They collapse under the force of gravitational attraction. They are attracted to each other at all times. The very initial stage when they are collapsing and trying to fuse, and some pressure is being generated outwards due to the fusion, that initial stage is known as protostar. The very initial stages when everything is collapsing, the gas cloud is gathering, some form of fusion is taking place, some pressure is exerted outwards, some is not. So that is a stage, or that is the day, or that stage is known as, in the life cycle of the star, as protostar. So the mass of the protostar increases generally, but why does it increase? So what I've done over here is that I've written down all the points from the book for the birth of a star, but I've also written down why it's happening, because you will not find the reason in the book. So as the mass of the protostar increases, but why does it increase? The mass is increasing because the cloud of dust is gathering or accumulating material throughout the space, wherever it can get it from, of cloud and dust, whatever it can get its hands on. It is collecting it because of the gravitational attraction. So even so that the gas cloud is collapsing onto each other, it's not done accepting or absorbing or calling for more dust or more gas of hydrogen from the universe. So the protostar's mass keeps on increasing. This is why it's happening. Generally then, as its mass increases, its core temperature also rises. Why? We discussed that just earlier, that over here the gravitational potential energy is converting into kinetic energy, and we know that kinetic energy is directly related to the temperature of a gas, or at least all the substances in the universe. So that is converted into kinetic energy, and as protostar contracts under internal gravitational forces. When the core is hot enough, which is of course millions of degrees, nuclear fusion can start and hydrogen is converted into helium and a star is born. But right now, this is not good enough for the birth of a star, at least maintain its life cycle. What has to happen is that once fusion reaction begins, they exert an outward pressure, and as long as the inward force of gravity and the outward pressure force generated by the fusion are equal or in equilibrium, the star remains stable. So with our sun, the inward force of gravity, that is because of its own mass, is equal, or whatever pressure it is generating is equal to the fusion that is taking place at the core, that is trying to push everything outwards like an explosion. So as long as both of them are balanced and both of them are equal, they exist in perfect harmony, and the star keeps on living. So next, we have the life cycle of stars. What happens with them? Right now, we discussed how they are born. But what happens with them as they keep on living through the universe? So there are two stages how the life cycle of any star in the universe actually goes through. So a stable star, which is, of course, actually starts from a protostar. Then when everything is in harmony and balance, it is known as a stable star. And the star is fresh, it is young, and it is living peacefully and in harmony. Everything is balanced, inward gravity, outward fusion pressure, everything is balanced. So star is stable right now. So when the star becomes unstable, now the question is, why does it become unstable? And the reason we will find that now what happens is that as the star keeps on living, it starts running out of hydrogen, because hydrogen is the fuel of the star, right? So now the outward force due to high temperature and thermal expansion is not good enough. Why? Because fusion is not taking place because you're running out of fuel, or fusion is taking place but it's not good enough, or it's not equally good or energetic as it was doing previously. So what happens, or what starts to happen, is that there are going to be two layers or two systems existing in the same star. You see, the inner core starts collapsing onto each other even more because that is concentrated in hydrogen. The outer layer or the outer side of the star, of the same star, cannot collapse in any further because it does not have any hydrogen. It's only made out of helium. So it stays, or you can say it starts expanding because of the energy provided by the fusion, right? And that is when we find the red giant. So the red giant is actually the very beginning of the death of the star, right? Again, let's go back. So the outward pressure is not good enough now because fusion is not taking place. So the gravitational attraction dominates, and the cloud experiences more gravitational attraction and starts collapsing onto each other. So wherever hydrogen is present, it starts collapsing onto each other. It keeps on reacting to become or to provide more fusion. But now, one interesting thing happens. Because hydrogen is very concentrated at the center and it is purely hydrogen, it starts to glow even more brightly. So, what's happening right now is that as it approaches its death, since less and less hydrogen is available, it starts to burn through it naturally at a higher pace. So, let's say when it was young and living properly, it was using, let's say, 1 ton or 300,000 tons of hydrogen per day or in 24 hours. Now it may be using up 500,000 or 100,000 tons of hydrogen, whatever is left. So the rate at which it is consuming energy starts to increase, which is why the red giant or this stage actually occurs, and it is sometimes more, even more brighter than the star's own life, sometimes. And the reason is because of that. Now, all of these details you will find in the next slide, right? But I'm just giving you a summary right now. So now it has two sides to live, or two such stages to exist. If the star in its original life was a low massive star, then it would follow this path until its death. If it was a very high massive star, it will follow this path until its death. Now, who decides which is a low mass and which is high mass? We didn't do that. We didn't do that. It's already naturally happening, but we did find out that generally approximately 8 to 10 times the mass of the sun is considered to be a low mass star, and anything greater than that will be considered as a high mass star, right? So whatever life cycle they go through, that will be decided by this. Okay, so what happens is that if it was a low mass star, the next stage it will experience will be a planetary nebula, white dwarf at the center. Why do we find a white dwarf? Because whatever hydrogen is left, even that starts to get or collapses under its own pressure or under its own weight, and as a result of all of that, it glows very brightly. So that came to be known as, or that is generally known as, a white dwarf. And we remember that dwarf is a word used for planets in the previous lesson, if we remember, right? So planets that are too small, just like the asteroid, right? And Pluto. Pluto was referred as a dwarf planet, right? So it forms a dwarf, white dwarf at the center, and the whole system is known as nebula, right? The next stage it goes to is a white dwarf, and eventually, when all the hydrogen is used up, even the last ounce of hydrogen atom, and everything is converted into helium, it becomes a black dwarf purely out of carbon. It's made out of carbon, and it just dies because it has nothing more to offer, right? On the other hand, if it was a very highly massive star, after the red giant stage, it will become a supernova. So what's happening at supernova stage? It's very interesting because sometimes we wondered or sometimes we questioned, of course at the very beginning of astronomy and the discovery of the universe, that where are all the elements coming from? Where did we get carbon? Where did we get iron from? Where did we get all the elements of the periodic table? Where are they coming from? They are coming from the supernova stage of the universe or of the star. But what's actually happening is that since it is very highly massive, it is so extremely massive that when at the ending days of its life, its own core is collapsing onto each other, the fusion is so strong, the gravitational field is so strong that even helium starts fusing to make other elements of the periodic table. And even those products start fusing to become something else. Even they start fusing to become something else. So when all of them and everything starts fusing together, that stage is known as supernova. And there comes a time and point when all of these respective fusion reactions release so much energy that it actually bursts or just explodes into a very big explosion. And when it explodes, all these, you can say, all these slivers of supernova expand or move through time and space, of course, and distribute all these elements that have actually been formed purely from hydrogen. So hydrogen kept fusing together to become helium, helium kept fusing to become something else, that daughter particle kept fusing to become something else, so on and so forth. So we find heavy atoms, or you can say heavier atoms of the periodic table, and we find their source to be supernova, right? Okay, so after that, once it has done or it is done with its explosion, there are going to be two more stages. One, sometimes even from the high mass, if it is just moderately high, then it will form a neutron star. But if it is extremely massive, let's say 20, 30, 40, or 50 times more than the sun, then the final product will become a black hole. That is how, and that is where a black hole actually comes from, right?